let me talk a little bit about how do you actually implement Jacobi and Gauss Seidel. Most of the time, when you want to adopt an iterative method, your matrix is very, very sparse, right? And it doesn't make sense to store the whole matrix in a dense form because the memory is going to be huge. And the modern computers are often limited by memory bandwidth as opposed to the number of floating point operations you have to do. So you don't want to store the matrix. Often you don't even want to store the sparse form of the matrix, right? So, for example, if I solve the Poisson's equation, I know my matrix is 1 over delta x squared using finite difference, minus 2, 1, minus 2, etc., minus 2, 1, 1, 1, right? So that's my matrix. And if I know this is my matrix, and in iterative methods, say Jacobi and Gauss Seidel, do I really have to compute that matrix, populate the matrix with just the minus 2s and 1s and put it in the computer? I don't really need to. So let me give an example for Jacobi and Gauss Seidel, how I can perform the iterations if I just know the value of the matrix on the paper without storing this matrix in a computer. Okay, so now I have the matrix on a piece of paper or in my digital paper. So, and I want to solve AX equal to some B. So Jacobi iteration, first of all, splits A into D plus OD. So my D is just going to be this times minus 2 and minus 2. My OD is just going to be this times 0 on the diagonal and 1s on the upper and lower diagonal, right? So let's apply Jacobi iteration. So D times x of k plus 1 would be equal to B minus my OD times x of k. So what you see is that what I need to do, I need to multiply my off-diagonal matrix with a vector. So by this time, I hope you're already very familiar with what we are actually doing when we are multiplying a matrix with a vector, right? So if we multiply this matrix with a vector, what are we actually doing, right? For example, look at the second row, 1, 0, 1. We are actually summing up the value on the left neighbor grid point and right neighbor grid point, and then divided by delta x squared, right? So the application of this guy, so OD times xk at the ith index, is actually equal to x of k I minus 1 plus xk I plus 1 divided by delta x squared. While here, if I start with the first index, I'm actually defining, so this formula would be true for all these indices if I define this xk at 0 and equal to xk n minus 1 equal to 0, right? So that'll generalize to the first row and the last row just by setting these to 0, right? This is like my boundary condition when I'm solving the Poisson's equation. Okay, so now I computed this. So the B minus OD times xk at I is simply BI minus that, right? There is not much. All right, so the next step is just inverting the matrix D, the diagonal matrix. So again, that's inverting the matrix is easy. It's just taking the reciprocal of these diagonal entries. So that would be minus delta x squared over 2. That's the reciprocal of the diagonal entries times my bi minus x k I plus 1 plus x k I plus 1 k over delta x squared. If you want to simplify it a little bit, you can just pull this out of this parentheses. The two minus signs cancel. You get the average of I plus 1. One of these should be minus, sorry. You get the average of it should be minus. You get the average of I plus 1 and I minus 1, the two neighbors, minus this guy times times bi. So that's Jacobi iteration, right? Very simple. You don't need to store the matrix in memory at all. All right. Okay. So how about Gauss Seidel? Gauss Seidel is a little bit. It seems to be a little bit more complicated, but not really. So Gauss Seidel. So Gauss Seidel, first of all, the explicit part is going to be only the upper diagonal. So let me say L plus U times x k plus 1 is going to be b minus u times xk. So evaluating the right hand side is even easier, right? So now I don't really want to write out the matrices because the upper diagonal is just the upper ones, the lower diagonal is just the lower ones. Okay, so this at the ith index, b minus uxk at the ith index is just the bi minus what? Delta, yeah, xki plus 1, right? That's even easier. Now the tricky part is, what do I do with that? What do we do with that is actually writing it out, right? And writing it out, basically d plus l xk plus 1 at the ith index is equal to, now the d part is just the diagonal, l part is my left neighbor. So that is simply my xk plus 1 at I minus 1 plus xk plus 1 at I over delta x squared. Oh wait, the L, the I has a minus 2 in it, right? Right? So that's it. That's the diagonal has a minus 2 and the lower diagonal part. Right? Okay, so now Gauss Seidel is simply saying that this is equal to this, right? Now we can see that doing forward substitution to solve this d plus l simply involves following this equation, starting from I equal to 1. So when I equal to 1, I know my x0, k plus 1, the boundary condition is equal to 0. So I can just solve for xi at k plus 1 immediately. And then advancing to I equal to 2, I already just computed the value at xi minus 1, which is x1. Then solving for x2 just follows immediately, right? So when I write down the formula, that's simply x of I k plus 1. Let's move this to the other side. Is equal to, okay, so first of all, the self term is equal to half of xk plus 1 I minus 1, right? So that's this term. And let's write down this is the implicit term. And the explicit term is, first of all, I have a plus, right? The two delta x's cancel. I still have a 2 here. xi plus 1 k plus, or actually minus because the sign actually changed. half delta x squared bi. Okay, so that's the formula for Gauss Seidel. Compare between this and this. The only difference is what? Yeah, the only difference is I have a k plus 1 in Gauss Seidel. I'm using the most recent updated value at the previous grid point. While for Jacobi, I'm actually using the old value, even though I just computed the new value at I minus 1, I'm still using the kth iteration value, right? That's what's happening for Jacobi. For Gauss Seidel, as soon as I compute a new value, I'm going to be using that value in iterating the next grid point.